Hi everyone, so here are your notes for 9.1, the Pythagorean Theorem. Let's go ahead and get started. Now, filling in these blanks. The statement says, in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. Now, just a couple things to note here. First of all, this Pythagorean theorem only works for right triangles. So if you don't have a right triangle, we cannot use this theorem. Next thing that I want to point out is this word square. The square of the length is referring to an operation. For example, c squared or 3 squared, which means 3 times 3, or b times b. This is what the word square is referring to. It is not referring to a box or an actual square. Okay. All right, and then we see this word sum, which means we're going to have to add the squares, there's that operation again, of the lengths of the legs. All right, there are two brand new words that I need to go ahead and define for us, and that is hypotenuse and legs. So in the right triangle, the hypotenuse is the side that is always directly across from your right angle. So if you can identify your right angle in the right triangle, then that should easily tell us where the hypotenuse is. All right, so my side AB right here is going to be my hypotenuse. Let me go ahead and write once more that definition down again. The hypotenuse of a right triangle. It is again the side across, or you could say opposite, from the right angle. Okay. The second thing that I need to note about the hypotenuse is the fact that it is the longest side in a right triangle. This has to do with the fact that it is across from the largest angle. Because again, in a right triangle, I cannot have two angles that are 90 degrees. And that also means that I cannot have two angles or even one angle that is a 90 degree and the other angle is greater than that. So it's quite impossible. All right, and then we have, of course, then the other two sides will be called the legs. Of the right triangle. Okay, now let's go ahead and let's actually get to our Pythagorean theorem. First thing that I want to do here is I want to label my side lengths of my right triangle. And the way we do that typically is we take a look at which angle the side is across from, and I'm going to label it with a little letter according to that angle. So the hypotenuse, which is across from angle C, will be labeled as little c. The side that is across from angle A, down over here, will be little a. And then, of course, the side across from angle B will be labeled little b. So again, keep in mind that these are side lengths. A, B, and C, little a, little b, little c are supposed to be numbers. So the Pythagorean theorem says this. It says that you have the square of the hypotenuse right up here. The square of the length of the hypotenuse. So I need to take the length of the hypotenuse, which is c, little c, and I need to square it. And this is equal to the sum, so that means I have an addition symbol in here somewhere. The sum of the squares of the lengths of the legs. So A and B represent the lengths of our legs, and we need to square them. So I'll have A squared, and I will have B squared. So this is our Pythagorean theorem here. You can go ahead and reverse the order if it's easier for you to memorize. We have A squared plus B squared is equal to C squared. Keep in mind, this will be extremely important later, that C is always your hypotenuse. All right, so let's go ahead and use the Pythagorean theorem in an example. So, for example 1, it says to use the Pythagorean theorem to solve for the missing side length. So our missing side length here is BA. And I can go ahead and write down my Pythagorean theorem, which says A squared plus B squared is equal to C squared. Now, just as I mentioned earlier, we always want to identify C, or my hypotenuse, first. So I see here that my right angle, angle C, and then I need to go ahead and look directly across from that to find, oh, here is C, little c, which is my hypotenuse. And once I know which side is the hypotenuse, then it doesn't really matter which side is A and B. Let me go ahead and just call 10 right here A, little a, and 5 will be little b. And then once we have our triangle labeled with the correct variables, it makes it quite simple to substitute in. So A is going to be 10 squared plus B, which is going to be 5 squared. And this is all equal to C, which is the side that we are missing. Keep in mind that sometimes we're not always looking for our hypotenuse. Sometimes we might be missing A or B instead. That's why it's so important for us to label our side lengths before we get started, so we know which side it is that we're looking for. So going ahead and continuing on, 10 squared is 100. Plus 5 squared, which is 25. This is, of course, equal to C squared, because I haven't done anything yet with that. 100 plus 25 is 125, which is equal to C squared. Now, the opposite operation of squaring a number or a variable is the square root. So to get rid of that squared, that C squared, I'm going to square root both sides of the equation. And then on the right side, my square root cancels out with my squared, and I'm left with the square root of 125 is equal to C. You need to make sure that you simplify the square root. I do have a video that I will link down below in the description on that shows you how to simplify radicals or square roots. So go ahead and watch that video if you need to, but I'm going to go ahead and skip that step. And here, the square root of 125 is going to be 5 times the square root of 5 simplified. All right, go ahead and pause the video here. See if you can give this problem a try on your own. All right, go ahead and double check your answers. Again, my suggestion to you is to always label your triangle, your right triangle, with A, B, and C first so that we know what it is that we're solving for. Notice how in this problem, my hypotenuse is again directly across from the 90-degree angle, and in this particular case, it is actually side PR, which we already have a measurement for. Our missing side is going to be B. If you went ahead and labeled this A, that's perfectly quite all right. We should still, at the end of the day, get the same final answer, which is 2 times the square root of 5, which is the square root of 20 simplified. All right, now there's something called the converse of the Pythagorean theorem, and this is kind of how it works. Let's go ahead and fill in the blanks, and then I can explain. So, if the side lengths of a triangle satisfy the Pythagorean theorem equation, then the triangle is a right triangle. So this is the basic idea. we know that the Pythagorean theorem, which says a squared plus b squared is equal to c squared, this equation only works if we do have a right triangle. But in this case, I don't know. I'm not sure yet if this triangle in the picture is a right triangle, but I do know the side measurements. So what I can do is I can go ahead and substitute these measurements in to the Pythagorean theorem equation and use this to verify to see if I have a right triangle. Let's go ahead and do just that. So first thing, of course, again, as always, is to label which variable is supposed to be C. Without a right angle, it can be a little bit difficult. But again, to remind you, the hypotenuse is the longest side. So if we look at this triangle ABC, we notice, oh, side BC, or the side that measures 5, is the longest side, so that's how we know this is C. And so then 3 and 4 will be, of course, A and B. Again, it doesn't really matter the order. Let's go ahead and substitute in. A, let me go ahead and substitute that in with 3 according to my labeling. 3 squared plus 4 squared is going to be equal to 5 squared. Now, again, we are actually checking to see if this will work. So I'm not entirely sure if this equation is actually going to be equal yet, because again, we don't know if we have a right triangle. But let's go ahead and let's finish up both sides of the equation. 3 squared is going to be 9 plus 16 is equal to 5 squared is 25. And then adding the left side together, we do get 25, which is in fact equal to 25 on the other side. And so because our equation checks out, both sides are equal, my conclusion about triangle ABC is that it is a right triangle. We have confirmed that because both sides of the Pythagorean theorem equation is equal, that the triangle that we started off with is in fact a right triangle. All right. Now, there is something that I wanted to mention down here, and that is something called Pythagorean triples. Pythagorean triples are whole numbers that satisfy the Pythagorean theorem equation. So just like earlier, where we substituted in the values for a squared plus b squared is equal to c squared, and we found that both sides were equal, these Pythagorean triples are guaranteed to satisfy that equation as well. And I like using these because they are whole numbers, because if we don't use these, we will most likely end up with a radical or a square root of some sort in the number, which is still workable, but whole numbers are very nice to work with. Now, one thing that I do want to mention is that these are not the only numbers or the only triples, of course. If I went ahead and if I multiplied all of the numbers in what's called a Pythagorean family by, say, 2, and I get these numbers, 6, 8, and 10, this is also a Pythagorean triple. I can do the same thing for this family, that's 5, 12, and 13. This becomes 10, 24, and 26. This family becomes 16, 30, and 34. And last but not least, the final family becomes, 14, 48, and 50. And then, of course, the list goes on because I can continue to multiply by 3. I can continue to multiply by 4, and so on and so forth. So there are technically an infinite amount of Pythagorean triples, but they do come from these original triples, or base triples, I guess you can call them. All right, so let's use this again in an example. In example 2, it's asking us to determine if a triangle with these given side lengths below is a right triangle. So again, in order to verify if we do have a right triangle, we can go ahead and do a squared plus b squared is equal to c squared. And we are checking to see if both sides of the equation are equal. The side that is the longest, which is 14 in this particular problem, this will be c, and the other two will be a and b. So substituting in, we get 7 squared plus 12 squared is equal to 14 squared. Finishing this up, we get that 49 plus 144 is equal to 196, or supposedly, that's what we're checking for. So 49 plus 144 is equal to 193. And this is actually not equal to 196 on the right side of the equation. So because the left and right side are not equal, my conclusion here is that this is not a right triangle. All right, moving on to example B. Now, something that's a little bit different with example B is this 2 times the square root of 3. We were working with whole numbers earlier, but this one doesn't give us a whole number. But I can still go ahead and use the Pythagorean theorem, and I'll show you how that works. The first thing I need to figure out is whether 7, 8, or 2 times the square root of 3, which one is the largest number to be C. Putting this into a calculator, so of course it is very handy if you have a calculator on hand. 2 times the square root of 3 is going to be about roughly, write it off here to the side, 2 times the square root of 3 is roughly, if you use the decimals, is about 3.5. So 3.5 is much smaller than 7 and 8. So what that means is our 8 right here will be C, because that's the largest side. So I have my Pythagorean theorem, which is a squared plus b squared is equal to c squared. Substituting in a squared, which it could be 7, plus, I need to use parentheses because the whole thing, 2 times the square root of 3 is getting squared. And this is going to be equal to, or I believe it might be equal to, 8 squared. All right, so on the left side right here, we have 49. And let me go ahead and quickly do this off to the side. But this is how we take care of 2 times the square root of 3, all of it squared. In this particular case, because we have multiplication going on, you can go ahead and square the 2, and then you can square the square root of 3. So this is what it looks like. This is equal to 2 squared times the square root of 3 squared. And this will get us 4 times, and again, keep in mind of what I said before in a past video on simplifying radicals. The square root and the squaring function, or squaring operations, cancel each other out. So I'm simply left with just a 3, and this is equal to 12. So in our original equation, we get that 49, plus 12 might be equal to 64. Finishing this up, we get 61 on the left side, and this is not equal to 64, which is on the right side. So because the left and right sides are not equal, again, I make the conclusion that this is not a right triangle. All right, so just to reiterate one more time, what I've done here is I'm checking and verifying to see, do both sides of my Pythagorean theorem equation, are they equal to each other? And if they are not, then we don't have any right triangles. Alrighty, take a moment, pause the video here, and see if you can give this a try on your own. Alrighty, go ahead and double check your answers over here. For part A, we actually do in fact have a right triangle because again, both sides of the equation are equal after we substitute it in. And then on example B over here, we had to figure out, first of all, is 4 times the square root of 5 the biggest side? I put this into a calculator, and that was around 8.9 or 8 9/10. So that is less than 9. So I know that 9 is supposed to be my hypotenuse, or the length of C. So substituting in here, again, off to the side, I went ahead and showed you how to square 4 times the square root of 5. We get that to be equal to 80. And then finishing up, we get that 96 is not equal to 81, which leads us to the conclusion that this is not a right triangle. All right, that's it for the Pythagorean theorem. Thank you so much for watching.